Okay, thank you very much for the invitation. It's a pleasure to be here. This is connected, no? It's right. Thank you very much for this invitation. I would like to to talk about a universality problem, right? We have a dynamical system. How should we think of the dynamical system? The dynamical system can be very wild. It can have periodic orbits or not. Today, I'm going to prove that any dynamical system can be embedded as a solution of the Euler equations, which are the equations that model the movement of incompressible fluids. Okay? So this looks quite surprising, but it's what I'm going to prove. For that, I'll need to go to higher dimensions. Not to infinite dimensions, but to higher dimensions. This is my excuse to be here. Okay, so let me recall what are Euler equations, okay? As I said, these are the equations that model the movement of fluids which are incompressible, okay? The condition of being incompressible, we can look at it. That's the thing, okay. We can look at it as a condition that the divergence is 0, okay? And Euler equations is a PDE, so I have an evolution of the system. Let me tell you what is everything here. X is the velocity of the fluid, okay? P is the pressure, and we have a PDE where I have a continuous evolution of the pressure. Unknowns are pressure and the velocity, okay? And I have a time dependence. And the condition that the divergence is free, in a way geometrically, it means that the flow of X preserves the volume, it's volume preserving. Okay, so these equations, we may write them like this, which is the standard way we look at Euler equations on the Euclidean space, right? If we have water, we don't think that there is some kind of metric associated to it, but there is a metric, which is the Euclidean metric. So we may as well change these equations and think of them on a Riemannian manifold, okay? On a Riemannian manifold, we just use a connection, a Levi-Civita connection instead of this formula here, adapted to a metric. If we replace any metric by the Euclidean metric, the result is precisely the classical computation of Euler equations. So we may be able to think of the movement of water on a system that you may think this is not physical, but we all know that some physical systems are not Euclidean. So we are going to be referring, and in this embedding problem of any dynamical system, I will be thinking of embedding a dynamical system inside the solution of this more general setup for Euler equations, where I have a metric. And I'm going to play with this metric. Okay, so that's the objects that I will work with. And now it's not too late to tell you that this is called dynamical systems in infinite dimension. I'm not going to be in infinite dimensions, and I'm not going to work as a dynamical system. Well, I'm going to be thinking of these objects from a geometrical perspective, though, of course, I will tell information about their dynamics. So, because I want to think of these solutions from a geometrical point of view, I'm going to consider a particular solution of the Euler equation, which are stationary solutions. So the solutions in which I don't have time dependence here, okay? So then the equations read as such, okay? We have divergence free, and the second equation reads as this. And then I can use the metric, that's why I say that I'm going to think as a geometer a little bit today. I'm going to use the metric to change these equations that I have there into some equations of forms, okay? Then I'm going to think of the rank homology of my manifold as an abstraction to solutions of these equations. And the way I'm going to convert from the first to the second line is by taking the solution of the Euler equations and considering the contraction with the metric. And this is giving a one form alpha. Alpha in all these slides is going to be the contraction of the solution of the Euler equations with a metric. Okay? Then these equations up there can be rewritten in the following format. First, the divergence in this more general context, because I want that the flow preserves the volume, the condition here, the volume is mu, and the condition is that the contraction of the solution with mu, which is going to be an n-1 form, it's going to be closed. Okay? So the condition that the divergence is 0 is the condition that some form is closed in a RAM homology of my manifold. And the first condition, I can translate it into a bit more complicated, that the contraction of X with the differential of this alpha, alpha is this 1 form, the differential of alpha is a 2 form, and again I contract with X, so I have a 1 form. I want that this 1 form is exact. And the function, so it's the differential of a function, okay, minus the differential of the Bernoulli function. So the function that integrates this 1 form has a physical meaning. It's the Bernoulli function, and the Bernoulli function depends on the metric because it's determined by the pressure plus 1/2 of the norm of the vector X. Okay, so the idea of using the metric to look at these equations, which are usually equations we think of evolution of vectors as cohomological equations, it's quite inspiring, and it's going to be very useful today. Out of the solutions of stationary solutions, I'm going to look at a particular class, which is quite general, thanks to our theorem of Arnold. I'm not going to enter there, which are Beltrami fields. Beltrami fields are vector fields that are proportional to their curl. We can define the vorticity or the curl of the vector field in this more general setup, just by generalizing the formulas. This is easy. And we also require that the divergence of this vector field is 0, okay? And well, many examples have this function that is constant, and then automatically you get that they are divergence free. But this is the general definition. So out of the stationary solutions, I'm going to look at Beltrami fields. And indeed, this looks like a very small box inside the box of dynamical systems, right? I'm going to embed a dynamical system as a Beltrami field by going to higher dimensions. Okay, so let's look at potential examples. Okay, so examples for compact manifolds. We have for the 3 torus, we have a very classical example given by the ABC flows that appear in KM theory. Okay. These are the solutions of these equations, and this is an example of Beltrami vector field, and also the Hopf field, which would be tangent to the fiber of the Hopf vibration, okay, and which we can express analytically, okay, as these vector fields. These vector fields are Beltrami fields on S3. Okay, so I said it, I'm a geometer, and I have to work with this kind of geometry, so I will be working more into contact geometry today rather than symplectic geometry, okay? So what I'm going to, my main trick today is to convert these Beltrami fields into a specific type of fields on a contact manifold. And this is going to be my game. My game is I want to solve some problem in dynamical systems. This problem is an embedding problem of a vector of a dynamical system as the solutions of the Euler equation. I'm going to embed them as solutions of particular type, which are Beltrami fields, which look very small box, okay? And I'm going to do it by associating to this Beltrami field something that is called the Reeb vector field of a contact manifold. So this is going to be my 1 minute of crash course on contact geometry. For a contact manifold, I will need to live in dimension, well, we are not in Germany, but we have the same system, right? I'm gonna do it. Well, this is not full of water. I failed all my attempts after all these years, living a lot of time in Germany, because I didn't have to teach, right? I had a perfect excuse not to be able to control the the karate kid of this cleaning. I failed, but it's okay. So, by the way, I was a bit quick. I started in dimension 3 for the Euler equations. And when we generalize to higher dimension, there is an analog for even dimension, but I'm going to consider odd dimensions here, okay? And this is good because in order to have a contact structure, I need odd dimensions. So what is a contact manifold? I'm going to take an odd dimensional manifold, and I'm going to start fixing a contact structure. And this contact structure, I'm going to assume that it's co-orientable. I'm not going to make a big deal of this. So I'm going to assume that it's given by the kernel of a one form. So I may think that I'm working with a pair of a manifold together with a contact structure. This contact one form satisfies one condition, that if I do alpha wedge differential of alpha to the n, this is a volume form. This condition looks very strange, but let me put an example. Let's assume that n is equal to 1. Then I'm working with three-dimensional contact manifolds. And what I'm requiring is the following. Alpha is a one form. Okay? If I look at the kernel of alpha, there are like two dichotomic situations. The situation in which I can integrate this kernel, and the situation in which I cannot. And there is a way to express this with the one form alpha. If I can integrate this, then this would be equal to 0. So when I have a contact structure, I want to consider the kernel of alpha, and I want this is a distribution, I want it to be non-integrable. For that, this cannot be 0, so I assume that this is a volume form, that this is different from 0. It could be negative or positive, okay? And that's my condition. So I think that this top form defines a volume form on my manifold. That's a contact structure, okay? And when I have a contact structure, you may think, this looks very strange. On any three manifold admits a contact structure. This is an old theorem. And it's very well understood when a general manifold admits a contact structure in higher dimensions, and the condition is almost contact. So it's very well understood what are the topological constraints for a manifold to admit this structure, but I'm not going to enter there. But what I need today is to define what is a Reeb vector field, and that's the only thing I need. A Reeb vector field is a famous vector field that I associate to a contact structure. If I think of contact manifolds as the analog in the odd dimension to symplectic manifolds that we have been seeing these days all the time, so a Reeb vector field would be a little bit inspired by Hamiltonian vector field. And what's the condition, how I define it? A Reeb vector field is a vector field that satisfies two conditions. That alpha is this one form, okay? When I apply it to R is equal to 1, and then the contraction of R with the differential of alpha is 0. How do I think of these two conditions? I think of these two conditions in the following way. The differential of alpha, okay, it's going to have a kernel because I'm on an odd dimensional manifold. And this kernel, okay, is one dimensional. So I have a vector field, I have a whole line of vector fields living there. So the Reeb vector field lives in this kernel, and this first condition is fixing, out of this kernel, is fixing exactly the vector field I want to take, okay? So these are what is called Reeb vector field. So you see, it's a specific type of vector field. And it looks very strange that if I have a dynamical system, I can always think of it as a Reeb vector field. It looks like very, very anti-intuitive, not intuitive. And the same if I have, a Beltrami field. This looks like two particular type of vector fields, the Beltrami field as a solution of the Euler equation, and the Reeb vector field associated to a associated to this particular geometry, okay? But it turns out they are going to be related. They are going to be related. If I have a Reeb vector field, I can always come up with a Beltrami vector field and all the way back. This is a theorem I'm going to use. And first, because I introduced the notion of contact structure, let me give an example. This condition, alpha wets the alpha volume form, can be satisfied, for instance, in the simplest case, in which I consider R3, okay, and I consider the basic form given by this, okay, which is the one I consider here. If I look at this, I may just check that everything makes sense. If I look at the kernel of alpha, this distribution, as you can check, is non-integrable, okay, because when I do the bracket of these two vector fields, I get partial of z, and partial of z cannot be written as a combination of these two. So this distribution is non-integrable, and I check that this is totally equivalent to this condition on the volume form. With this alpha, this is an easy check. This is an exercise that this gives me exactly the volume form I want. Okay, so this is the easiest example of contact structure, and indeed, locally, it's the only example, because there is a theorem that tells me that locally any contact manifold of 3 dimensions can be written, I can find coordinates, local coordinates, such that this is the example. So if I am interested in making computations locally, that's enough. That's the example I need to think of. Why do you need contact geometry? Well, maybe I need contact geometry to park my car, right? You say, how is this possible? Well, Emmy Murphy, who is a prestigious contact geometer, she proved this, that a car, this is a kind of joke, but it's a theorem indeed. A car of length L can be parallel parked in any space of L plus epsilon, and she proves this using this contact form, okay? We all know what happens when epsilon goes to 0, okay? So this is the joke of the talk. But, okay. Now let's go back to this example, the example I gave of Beltrami field, which is that of the Hopf vector fields, okay? Now I want to relate these two different types of vector fields, Reeb vector fields and Beltrami fields, which look very different. One lives in a contact manifold, the other one is stationary solution of the Euler equations, so it's a particular solution of the movement of a fluid. How can they be related? So let me show first an example of a vector field that is both Reeb and Beltrami, and this is the ones of the Hopf vibration. I'm going to take, in order to do this, I can take this one form here, okay, on the 3 sphere, and then I compute the Reeb vector field. It's an easy computation that you can do before breakfast, and you get this vector field. Now, if you write down who is Uvar and everything, oh surprise, you get exactly one of the Hopf vector fields that I showed before, okay? And indeed, this vector field, as I said, is Beltrami. I said it and I didn't check it. A way to check it is to use some kind of adapted coordinates, which are called Hopf coordinates, in which you can really see the vector field already with constant coefficients. When this happens, automatically you know that the divergence is 0 and that the vector field is parallel to its curl because of this tree. So on S3, right, if you take Hopf coordinates, then this Hopf field automatically, because it's constant on these Hopf coordinates, is a Beltrami vector. So this is the same vector field with 2 different parametrizations. One is a Reeb vector field, and the other one is a Beltrami vector field. It's a coincidence or not? So let's ask the experts. Okay, so we have here Arnold and Sullivan, and indeed it was Sullivan who observed, Dennis Sullivan, he observed they should be connected, right? He observed it, but he didn't prove it. Who proved it? Endar and Greist. Endar and Greist proved that there is a one-to-one correspondence between Reeb vector fields and Beltrami vector fields. Okay? this correspondence, it's quite subtle. Why? Because these Reeb vector fields and the Beltrami vector fields are associated to an additional structure. So we have like two words. Here we have the contact wall, right? I should have colors. And the contact wall should be pink, right? On the contact wall, or magenta, or let's see what this gives. So on the contact wall, I have a Reeb vector fields, and I have contact one form, Reeb, and this contact form. And then I have the Beltrami, the world of Euler equations. And of course, this world should be blue, right? Because it's water. So then there, on the Beltrami side, on the fluid dynamics, here I'm going to take a Beltrami field. And don't forget that associated to this Beltrami field, I have a metric. So in this theorem, in this association, associated to alpha, they're associated to the pair, Reeb vector field and alpha, you get a Beltrami field, but also a metric. And this association depends, really, it's very important to get to follow the role of the metric on one side and alpha on the other side. And this is going to be important. Because, for instance, if we are able to apply our techniques in contact geometry, one of them is the H principle, which deforms this alpha. On the other side, I will have to deform the metric. This means that I'm going to be changing the metric drastically, and maybe I cannot prescribe it to be the Euclidean metric. And this is going to be an important part of my game. Okay, so this pink to blue correspondence is exactly what Ednar and Grice proved. And indeed, the proof is very simple, because if we look at the equations, these are the equations of Beltrami fields that we express using the language of the RAM forms. If we look at this expression here, then who is the candidate for the contact form? If I have a Beltrami field, the candidate for the contact form, it's erased here, and that's the game changer, is precisely the contraction with respect to the Beltrami field of the metric. This one form turns out to be contact. And why it's contact? Because these two conditions are satisfied. And that's the important part, okay? So I'm going to be using today a lot this kind of correspondence that I usually call the mirror, because it's like a mirror, okay? You want to solve something in fluid dynamics, and maybe you are a bit better at contact geometry than fluid dynamics. Then you cross the mirror, you solve it in contact, and you come back. And this is what I'm going to do today to prove this embedding. Okay, so this is a theorem they prove, and it's a mirror like in this picture here, okay? Where I think, indeed, I could think of the sky as contact geometry because many movements in celestial mechanics, I can control them with equations that come from contact geometry. And on the other side, I can see the fluid dynamics, right? So indeed, this mirror is really, this picture would be the mirror. So this has been very fruitful, this correspondence, and there is quite a lot of things that I can do. And today I just want to indeed, my point was to prove, to embed dynamical systems as these Beltrami equations. How I'm going to do that is I'm going to use this correspondence, and here I'm going to apply the H principle. But before that, because the idea is that I really want to, convince you that this makes some sense, I'm going to do it with particular systems. For instance, I'm going to give, a fluid version on the n-body problem. So I'm going to take some actual systems, dynamical systems, and I'm going to present them as solutions of some Euler equation. They are going to be stationary solutions. And once I have convinced you that these two realms are close, then I will tell you how to prove the theorem, okay? And of course, I'm going to have to hide things because the H principle, if I give the details of the proof, we will never leave this room today. And this is not the plan. So I will just use the H principle, as a toolbox. It's not a toolbox. We had to work very hard to do that, but it's not the moment, I think, to give many, many details. So let's go on. Let me convince you about this, because of course, here, because I have this correspondence, if I know things about the dynamics of the Reeb vector fields, for instance, existence of periodic orbits, then I can extrapolate it, and I know things of the dynamics of Beltrami fields. So I'm going to start talking about the existence of periodic orbits for dynamical systems. And I'm going to focus on the odd dimensional case. I'm going to start with the conjecture of Seyfert, which is a conjecture in the 50s, which tells us that every non-singular continuous vector field on the 3-sphere has a closed orbit. This was a conjecture. People believed this was true. And then this was the Pulse-Weiser, who you can find. This is here we have Seyfert. Okay, here we have Pulse-Weiser. He found a counterexample which was C1, right? And then this counterexample was from 74. And then it took a long time to find a C2 counterexample. We know how life is for a mathematician, right? So this was proved by Harrison in 88, okay? And then, let's say, people were giving these counterexamples, but the smooth counterexample was proved by Christina Kupperberg in 94. So she gave a counterexample to this conjecture. And this counterexample is based on a kind of Planck construction like this one, okay? That if you have a periodic orbit, you are able to kill it by putting this kind of Planck here and trapping it. Okay, and it's quite interesting. It's very interesting, this construction. But as you can see from the conjecture to the counterexample, we have long time. Okay, so the question is, okay, it's true that Christina Kupperberg found a counterexample to the Seyfert conjecture in 94, but the question is, okay, this is because you consider any vector field on the sphere that has the condition that is non-singular. Now, the question is, are you considering a specific type? What if I consider a specific type of vector field? For instance, a Reeb vector field, because the 3-sphere is a 3-manifold, as I told you, any 3-manifold admits a contact structure. So if I take the Reeb vector field, will it have a periodic orbit? So it's a natural question, right? So that's the question. In particular, by the way, a Reeb vector field, it's always volume preserving. It has this property because I took the volume to be alpha what's the alpha, and the Reeb vector field preserves alpha. Okay, so that's the question, and indeed there was another conjecture just for Reeb vector field, which was posed by Alan Weinstein, which is that the Reeb vector field of a contact manifold admits at least one periodic orbit. Alan Weinstein put it in a context of systems that really came from mechanical systems. He was interested really in down-to-earth problems, and this has become one of these important conjectures together with, let's say, in contact geometry, there is this Weinstein conjecture, and let's say in symplectic geometry, the analog would be the Arnold conjecture. So this has been one of the guiding lines. And there have been, like, this conjecture was posted in 88, no, before 88, now 83, I don't remember exactly. But this was proof, let's say, for the hypersurfaces on R21 with a standard symplectic form, this was proved by Viterbo in 88. And then for the 3-sphere, this was proved by Helmut Hofer, and his proof used pseudomorphic curves. So he uses from contact, he goes to symplectic by contactization, and there he uses these famous tools in symplectic topology. But the real proof in general for any 3-manifold comes from Tops in 2006. And this proof is quite incomprehensible in the sense that it uses a lot of tools. In particular, it uses Seiberg-Witten equations. So in order to prove this, and it's like very interesting that if you want to understand the proof, maybe the best solution is to read a paper by Hutchins, which explains in whole detail the proof of Thomson. And indeed, one vector field is not sufficient, because if you think about the movement of the planets, right, then there are many infinite periodic orbits. So just to wait for one, expect one is not sufficient. Indeed, Dan Cristofaro Gardiner and Hutchins proved in 2016, so this is less than 10 years ago, that every Reeb vector field has at least 2 periodic orbits. But then we go back to the examples in celestial mechanics. So Reeb vector fields generically tend to have infinite periodic orbits. So the conjecture has now jumped from Weinstein conjecture about the existence of 1 periodic orbit to the conjecture that tells you there are either 2 or infinity. And the case in which it's 2, it's well understood. It has to be a length space. Otherwise, there are infinite number of periodic orbits. And this has been proved by Vincent Collin, Pierre de Hornoy, and Anna Rechman very recently, okay, that every Reeb vector field with some conditions, which you call non-degeneracy, which are of the same type for dynamical systems, it has either 2 or infinity. So you have this, let's say, if you want to understand, if you can embed any dynamical system, you want to understand what happens to the periodic orbits. So for Reeb vector fields, you have this kind of results. And if you have it for Reeb vector fields, thanks to this correspondence proved by Ednar and Grist, you have it also as an application of the mirror for any Beltrami field. So Beltrami field has the same properties, okay? You have these 2 or infinite number of periodic orbits if you meet this non-degeneracy condition. So why, well, I mean, I have been explaining here all this, and of course it makes sense to try to understand if you can embed dynamical systems into a bigger set, because you want, in a way, to organize your dynamical systems, right? To put them in boxes. You get to your house, you look at your apartment, and you say, oh, I want to organize my apartment. I want to have a big box where I can put dynamical system, and if I can, you know, put a label to this box and saying, these are Beltrami fields, this is very cool. But the motivation for us to look at this problem is not organizing my room, okay? The motivation came from a question by Terence Tao, okay? And the question, he asked if any incompressible vector field, so volume-preserving vector field, can be embedded as an Euler flow by increasing the dimension of the manifold. So he was asking this question, but his motivation was not putting labels on dynamical system. His motivation was finding a counterexample to the conjecture that the Navier-Stokes equations have regular solutions, okay? So as you know, well, I talked about the Euler equations. These are equations that where the fluid that you consider doesn't have viscosity. If the fluid has viscosity, these equations are no longer Euler, but are called Navier-Stokes. And you know that you can get a lot of money if you prove that they have a solution for all time, or that the solution explodes. This is still an open problem. This is one of the problems on the millennium. So you get money, you get fame, you get a lot of things, if you can prove or disprove. However, people have not been able to do it. And Terence Tao, who thinks many things by the minute, thinking about many things during the day, then he thought, I have an idea. Maybe if I can, he said, maybe if I can represent any incompressible vector field as a solution of the Euler equation, this helps me to find the blow-up, okay? More concretely, his question is it possible to construct Turing-complete fluid flows? And his motivation was the following. In order to achieve blow-up, he was suggesting to take initial conditions that were complicated enough. This is what we are going to call Turing-complete. I will not enter much onto this, in such a way that, because the system is very complex, when you get the evolution of your system, you can get the blow-up. So he asked this. I saw this on Twitter. He doesn't have a Twitter account, but somebody posted it on Twitter from his blog. What's the title of his blog? WhatsApp or what something? What's the title of his blog? I forgot. what's the, I don't know, he has a blog. And somebody posted it, and then I was on the train, I was bored, and I thought, we had been working on this with Daniel Peralta Salas and one of my former students, Robert Cardona. So then I thought, let's try to apply the H principle to this, and let's see if it works. Sometimes you have crazy ideas that don't work most of the time. This time it works. So we were able to answer this question. Is it possible to construct two incomplete fluid flows? Yes. And we were also able to answer this question. So we sent out an email. Look, we have been able to prove this. And first he said, oh yeah, but you are constructing a time-independent. I want a time-dependent solution. This is not my question. And we were, oh, he doesn't like it. And then we sent him the other construction. He said, oh, this is cute. So we have been getting this kind of answers. Still, we have answered these questions, but this doesn't give the blow-up, okay? So, okay. So let's go back to the initial motivation comes from this question of tau, and I could come back at the end of the talk maybe, but the answer, I mean, just to simplify, is that this path didn't work so far, okay? We have not been able, I mean, tau has not been able to produce a counterexample, as you know, of the Navier-Stokes. And at this moment, there are many people working on this from different perspectives and using machine learning too. And it's a quest for that. And it's very interesting to see how this evolves. But let's go back to our leveling of dynamical systems, right? So the idea is now we have been looking at some examples. These Reeb vector fields, they always have periodic orbits. So this idea of, increasing the dimension of your manifold, and you have a dynamical system, and thinking that you can embed on a bigger dimensional manifold, if I have to explain it in simple words, it would be like this. If I ask Midjourney to make a picture of Barcelona in January, Midjourney produces a sunny day. If I ask Midjourney to produce a picture of Vienna in January, there is a snow. By the way, it was snowing, but we have not seen this picture yet this week. So this looks very different, right? But the idea of, in a way, universality is that if we are very far away, we are not going to see the difference of the two dynamical systems. We are going to see them alike. In a way, if we go to the outer space, from the outer space, we don't see so much the difference. These are just points of light on the outer space, Vienna and Barcelona. So, okay, now, this was philosophy, but let's go back to business. I want to convince you, first I'm going to prove it using the H principle, and then I'm going to do abracadabra. Nobody's going to understand what's going on. So let me convince you that I can do this with some systems, okay? So you give me a dynamical system, and I'm going to put it as a solution of Beltrami fields with my hands, okay? But, okay, you are not going to give me this problem because I wouldn't be able to do it on the spot. I choose the problem. So I'm going to take the Kepler problem. So I have a planet orbiting a star, and, well, this is a Hamiltonian system. This is the Hamiltonian, okay? And then, well, this problem is initially symplectic, okay? Where does contact geometry comes in? When I restrict to certain level sets of, if I restrict to, indeed, in the Kepler problem, to an arbitrary level set, I'm going to get a contact structure. For that, I need a condition of having a Liouville transverse to this level set. So if I start with a symplectic manifold, I have even dimension. I take an hypersurface. I have odd dimension, so good. I can try to see if the restriction has a contact structure. And how do I see it? If this hypersurface has a vector field transverse to it that has the property of being Liouville, I take this vector field X, I contract my form omega, my 2 form, and I get my contact form alpha. Okay, so I'm going to take the Kepler problem, okay? And the Kepler problem, or the regularized version, so I don't have collisions, is known, and this is a theorem of Moser or Sipov, Abel, Bruno, results from different people, that depending on the level sets, if they are 0, positive or negative, the level sets of the energy, the dynamics of the Kepler problem is equivalent to the cogeodesic flow on the spherical cotangent bundle on a 2-sphere if the level set is negative, on the plane if the level set is 0, and if the level set is positive, to the hyperbolic space. This is a nice presentation of the Kepler problem geometrical, okay? And it's convenient for us because it plays with the spherical cotangent bundle. So I take the cotangent bundle and I take the covectors that have unit norm, okay? So now I want to understand this model, okay, as I want to understand the dynamics of the Kepler problem. So the Reeb vector field of the contact structure that I have here, because the spherical cotangent bundle has the right dimension, okay? I want to understand this Reeb vector field as a Beltrami field. What do I need? I need a metric. So I need to understand the metric, and a miracle occurs. If I have a Riemannian manifold and I consider the spherical cotangent bundle, then the Reeb vector field of the Liouville form restricted to the spherical cotangent bundle is Beltrami with respect to which metric? Well, I'm on a spherical cotangent bundle. So the canonical thing I can do is to take the cotangent lift of the metric. So I have a Riemannian manifold with a metric, okay, and the cotangent bundle, I can lift the metric. So I lift the metric and I restrict to the spherical cotangent bundle. And this gives me a metric, and the big surprise is that this metric is the right one, in the sense that the Reeb vector field of this contact manifold indeed is Beltrami with respect to this metric. Miracle. This is very practical because instead of writing that it's a theorem of Moser and Belbruno and Osipov, here I put some Spanish people, Fontana Magnali, he looks American, but he's Catalan, and Miranda and Daniel Peralta Salas. What we did is really to use this trick to present the Kepler equations indeed as a solution of the Euler equations, okay? So here I don't do H principle, I don't do magic, it's very easy because I can identify the Reeb vector field as a Beltrami field because these spherical cotangent bundles come automatically endowed with a metric. And I can use this metric. This metric is just the cotangent lift to the cotangent bundle and then the restriction to the spherical cotangent bundle. So the Riemannian metric is exactly what I just described. And then, indeed, I can think of the symmetries of the Kepler problem as isometries with respect to this Riemannian metric. So this would be the version of the Kepler problem as a solution of the Euler equation. And this works, indeed, not only for the Kepler problem, but for any mechanical Hamiltonian system. If I take an energy level that is above the maximum value of the potential, okay, then if this happens, automatically the level set is endowed with a contact structure, and I can play my game. So in particular, it happens for the n-body problem, okay? The problem is that here, the n-body problem, we know there is an adapted Riemannian metric, but I cannot describe it as beautifully as in the Kepler case, in which I can just say that the metric that makes that vector field Beltrami is the cotangent lift. Here, there is a metric, but it's more complicated. However, okay, if I can put the n-body problem as a solution to the Euler equation, I'm happy, okay? But let's be ambitious and let's put any dynamical system. Let's go back to the initial question. So this is just some examples to train your mind to think, yes, I can think of this as solutions of the Euler equation. Now, let's go back to the question of tau. Can an incompressible vector field be embedded as the Euler flow in higher dimensions? We translated this together with my student Robert Cardona and Daniel Peralta Salas and Francisco Presas, who is the expert in contact geometry from whom we learned all these H principle tricks. Can we realize a vector field on a manifold? That's our translation. As a Reeb vector field on a bigger, compact contact manifold. So the question of tau is in blue, and we translate it in pink, okay? And we try to answer this question. Indeed, we started to think with this question with Robert and Daniel. And then, of course, initially I thought, well, if you have a vector field, what are the conditions of these vector fields to be compact? Of course, you start to come up. This vector field cannot have zeros, blah, 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 blah. And I had, we thought somebody must have thought of this. So I sent a WhatsApp to Fran, and I said, look, is this true? And Fran said, no, this is false. and then 2 hours later, this is very interesting. I'm going to think about this. And then the day after, I couldn't sleep. I think this is an interesting problem. So this is how Fran joined us, okay? And then, well, what we realize is that the condition, you start thinking about this, the condition that you need is that the vector field is geodesical. What does it mean that the vector field is geodesical? It means that this is a vector field such that there exists a Riemannian metric such that the geodesics, all the orbits are geodesics. And indeed, you can take them to be geodesics of unit length. If you translate this in equations, you have two conditions, alpha of x equal 1, and the contraction of x with the differential of alpha equals 0. And now you're going to see, oh, but this is very simple. These are the equations of the Reeb equation, so solution, you got it, geodesical equal to Reeb. No, because this alpha doesn't have to satisfy this condition. So that's exactly the trick. If we have a geodesical vector field, okay, we have an alpha satisfying these conditions, but we don't know if this alpha is a contact form. So the idea is that, okay, take an alpha and try to deform it to get a contact form. And this idea of deformation is precisely the H principle. So once we thought about this, we realized that you need this condition, and is this condition sufficient, and how hard is to get a geodesical vector? Well, if you don't move from your space, it's a condition, it's hard. But I have the freedom to go to higher dimensions because this is a workshop of infinite dimensions. I'm going to start with finite dimensions, but I'm going just to go up in one dimension. The answer to question 2, how hard is to get a geodesical vector field, is it's not hard. Okay? The answer is just by increasing one dimension, I get a geodesical vector field. So that's the lemma. If I take a periodic vector field, and if it's not periodic, then the embedding is not going to be compact, but I can still play games. Then, well, if I increase one dimension, is automatically, and I take the suspension trick, the one form given by the suspension, the differential of alpha, is the one form I need. So it's geodesical, okay? So the condition of geodesicability, if I allow myself to increase the dimension, it's not a big deal. Now, I need to deform. So the idea is, I have a form alpha satisfying these equations, but I don't know if the condition of contact is satisfied. The idea is, can I perturb this and get a contact structure? So this is a question about flexibility and rigidity in contact geometry. So the experts, the absolute expert in this is Yasha Liasberg, and indeed he proved a very important theorem with Borman and Murphy, which is that the characterization for a manifold to be contact in dimension 3, any manifold can be contact. Higher dimension, you need a constraint, which is called almost contact, which doesn't ring a bell, but it's a condition essentially that's saying that you, instead of having the differential of alpha, you have a two-form alpha omega such that this is positive, and then you want to deform this omega to the differential of alpha in a way. And how did they prove this theorem? And this was the inspiration for our proof. They prove it with the 3 steps of the H principle. The only thing I can do today about the H principle is talk about the philosophy. The philosophy is I want to solve an equation. I cannot solve it. So the semi-goal is I solve the linearized version of it, which is called the formal equation. And the miracle is I can deform a solution of the formal equation to an actual solution. In their case, they had an almost contact, so they had this omega, and they could deform this omega to the differential of alpha. And they do it with this H principle, which is really, today it's going to be a black box. So there is a picture of Gromov because Gromov and Eliasberg are the ones who introduced more or work more the H principle in contact geometry. So indeed, this is a slide I'm gonna skip, but this is absolutely technical. The idea that we do is we have a vector field, and we want to embed this as a Reeb vector field. Okay? So my idea is we take a geodesical vector field. I have this alpha, and I need to deform in a way to a contact form. And it's a black box today, but this was a lot of work, and I thought I wanted to put a slide. but today maybe it's not the day to talk about this. But we were able to, in a way, our proof, the H principle that we proved, boiled down to a technical lemma of the proof of Eliasberg and Murphy and Borman by increasing a certain codimension with an isotropic subbundle. But I'm not going to go into details. Let's go back in business. I can erase. What did we prove? Well, we proved, the other examples that I gave you today are convincing. The Kepler problem, it works. N-body problem, it works. In general, we proved that the Euler flows are universal. So if I give you let's say, if I give you a dynamical system, I can always embed it, okay, as the solution of the Euler equations, and indeed as Beltrami fields. For that, the target space is going to be compact. Here I put a sphere, but it could be any compact space, or Rn, depending if the vector field you have is periodic or not. If the vector field is periodic, is periodic in T, these are the conditions. I skipped the former one. You take an autonomous vector field, and in the T coordinates, if it's periodic, then I can embed it, which would be this condition here. I can embed it on a compact manifold. Otherwise, it's going to be embeddable on Rn, okay, for a higher dimension. So what is the dimension? It's not infinite dimension. I start on a dynamical system in dimension n, and I embed it on a manifold of dimension 3, dimension n plus 5. Let's say the smallest one of these numbers, because it has to be odd, because it has to be contact, right? Or Beltrami, if you want. So it has to be odd dimensional. One of these two numbers is going to be odd. So this would be an upper bound for this embedding. Of course, first time I presented this result was in analysis seminar in Zurich. I was very excited to talk about this. I thought I had done an important thing. But then the people in Zurich told me, what about R3? You start in R3 and you go very, very far away. We are not interested in leaving the three-dimensional space. So this took us to the next step that I will explain. But what is the idea of the proof? If we want to prove this, well, first, want to prove this, can you assume that the metric is the Euclidean one? No, because in this business, if I deform alpha, I deform the metric. However, you can assume the metric is a perturbation of the Euclidean metric somehow. But what is the karma of the proof? Well, the karma of the proof is, first, I'm going to cross the mirror. I'm going to present this dynamical system as a Reeb vector field, okay? And then I'm going to cross again and translate it as an Euler solution of the Euler equations, okay? So step one, right? Using the correspondence, the question is universality of high-dimensional Reeb vector fields. Can I embed in this universality? And step two, well, we know the Reeb flows are geodesical with respect to the adaptive metric that makes them Beltrami, but the other way around is also true. If you have a geodesical vector field, you can always find higher dimensional manifold such that the push forward of this vector field is Reeb. And how far do you need to go? Well, you do a kind of construction which implies a cotangent bundle and some Gromov things. So you need to go to 4 dimension of n minus 1. This is a monster, that dimension. If you start in dimension 3, then you go up too high. And then you can improve this dimension, and this is where you use the H principle to sharpen it. Here there is an H principle already because you use a result of Gromov that uses the H principle. But then we needed to come up with an actual H principle to reduce this dimension. Okay? And what we could do is that we could reduce this dimension in the case in which the contact structure is over-twisted, which is a famous type of contact structure. If we get a better result, but otherwise we get 3 dimension of n plus 2. So we improve a little bit. How much? 5. Okay, now with that I can finish. And the final step, okay, is, well, exactly. I mean, let me see, what did I do? Okay, I have a so if I have geodesimal, I can embed it, and if I don't have geodesimal, I just take the trick of the suspension first. This will increase one extra dimension. So putting everything together and adding the one dimension that I add for the suspension, I can go up to, one of these two numbers is going to be odd, and one of these two numbers is my upper bound, okay? So this is how we prove this. And then we go back in these last minutes to the question of tau, the initial question of Turing completeness. Why? Because we wanted to find also a counterexample of Navier-Stokes. We also want to be rich. Well, indeed, we didn't do it for that, but we wanted to find this condition of Turing completeness. The condition of Turing completeness is, in easy words, is that as I move in the dynamics of my vector field, this is the same as computing on a Turing machine. How do you do this? In a way, I associate to the movement of the particle, I associate a computation, okay? And why is this useful? Because if I have a dynamical system to which I can associate a Turing machine that can reproduce any computation, which is called the universal Turing machine, and this condition we call Turing completeness, okay? Then I have a kind of superpowers of initial conditions. I have a way to produce many initial conditions for Navier-Stokes. You say, oh, but nowadays we can use machine learning and ChatGPT and blah, 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 and artificial intelligence. Yeah, but here you have a counter of it. So that is a condition of Turing complete. And first we answer the question of Terence Tao. Terence Tao had given in his paper an example of a dynamical system which was Turing complete in dimension 4, okay? So by using our trick, by using our up and bound, we were able to construct initially a Turing complete flow on a sphere of dimension 17. I was very proud of this construction. Again, go to an analysis seminar in Zurich and you are killed because they say dimension 17, are you kidding? So the question was natural. I came back from Zurich and I told Daniel, I was totally unsuccessful. They want an example in dimension 3. So that's the last thing we did. Indeed, coming back from Zurich, we realized indeed that we could find a three-dimensional Turing complete Euler flow. This is not an embedding theorem, but it answers the questions of Terence Tao, so you get extra points. And we were able to prove that there is a three-dimensional solution of the Euler equations in stationary, which is Turing complete. And then this gives an interesting corollary that was maybe what, I mean, with this Turing complete system, we tried to find the blow up. Indeed, we could plug the equations and see the evolution because the Beltrami fields collaborated in a good way, but there was no blow up. Okay? However, an interesting consequence of associating a Turing complete system or a Turing machine that is universal to a dynamical system is that you get trajectories that are undecidable. Because the halting problem is undecidable. This is something Turing proved. And the condition of Turing completeness, in a way, is that entering an open set is equivalent to the halting. So the trajectory, it enters an open set. This is equivalent to the Turing machine halting. Because the halting problem is undecidable, entering this open set is an undecidable. So we were, this as a corollary, we were able to prove something that was not known before, that there exists undecidable fluid paths as a consequence of this. And with this, I finish. Thank you very much.